Now, if we just talk generally about argument passing, as we look with this system, you can think right away there are a couple of things that you can do. You can use the registers. That's probably the easiest way. However, you can quickly run into problems here because, note, register 7 is for your return address. So you can't use register 7 to pass an argument. If you put something in register 7 and then call a subroutine, what you put in register 7 just got lost because it was replaced by the program counter, your return address. So you can't use register 7 to pass things. Register 6 is generally reserved as a stack pointer. Now, if you're not using the stack, okay, you can go ahead and use register 6 however you want, and you're okay. But typically, there's a problem there, which leaves us with these registers 0 through 5 for argument passing, and it means we're limited to 6 values. So that's the big limitation in using the registers. If you have 6 or fewer, the registers are definitely the place to do it because it's faster, it's easier, accessing the values within the subroutine is a piece of cake. So we can do that. But if you have more than 6 values, you've got a problem. So one of the ways to do it is to have dedicated memory locations, places where you put this information. The problem here is that basically you're talking about global variables. Because what you're saying is that the label on that memory location where I've got the argument for this subroutine is accessible from any part of my program. That label is common to everything. It's a global variable. That's really what we mean. Now, there are some other ways that you can use memory. That is that you can have, let's see, I'm going to try and write a little bit of code to do this. One of several blocks of memory, and you send the address of the block in a register. Okay, are we beginning to sound like something that you might have seen before, like pass by value and pass by reference? That's really what we're talking about. Really up here, you're probably doing pass by value. You're giving the subprogram the values that you want it to work with. Here, they are in memory someplace, and yeah, they're going to be common. If I change something in the subprogram, it's going to be changed in the main program because what I'm actually sending is an address. the other option that kind of uses memory, but is more commonly used, is to pass values on the stack. And again, you can either put the actual value that you're going to work with out there, or you could pass an address of a location, pass by value, pass by reference. Just all depends on what you're giving the program. Just so that you recognize how things work in all the C-related languages, what happens when you pass an array? You pass arrays by value or by reference?
Reference is
Reference.
ideal.
Why? Because typically in those arrays there are so many of them, so many actual elements, so much memory being used, that setting up another copy of the values to pass is more than just a little tedious, and it occupies a lot of memory, and you can bypass that simply by passing the starting address of where that array is located. Big. So you always pass arrays by reference. That's the way they work. Now, where do you pass that reference? You can put it on the stack, you can put it in a register, wherever. Okay, I'm going to do, at least start on, we'll see how far we get. A little program here, and I'm going to use this method simply so that I can demonstrate it. You'll see that the number of values that we're going to pass isn't that much. It isn't that big a deal. But it just help you see how we can actually use that stack as a means of getting information. Okay, here's the problem. It can be stated very simply. Take the 2's complement value in X, print it in base 10. Okay? Nice simple little problem. Really easy to understand what we're trying to do. Now I'm going to set this up so that I can handle either positive or negative numbers. That's something we haven't looked at before this. So let's just work with that. Just see how much of this we can handle. If we have a 16-bit number, which is what we're limited to with the LC3, how many spaces out there am I going to need? How many digits can I potentially get out of a 16-bit 2's complement number?
65.
No, it's bad. What?
5.
15.
Yeah, which is how many decimal digits?
Yeah, it's 5.
5. The largest number is 32,767. The smallest one is minus 32,768. So I'll need 6 characters. Let's just note that here. So as I start setting up my character string to print the thing out, I'll set up 6 memory locations. Okay, so I will initialize something that looks like this. My string will say I'm going to terminate that string with a 0 byte, or a 0 word, a null character. Remember that? That's a nice signal to our printing systems that we're done. Now, what am I going to fill in there? I'm going to initially fill all those spaces with spaces. That's a hex 20. Now, what I'm thinking as I do this, the reason I fill all those things with spaces is that I'm going to right justify my number. That is, it's going to be on the right side of that 6-space column. And so if I only have 3 digits, then I want to print 3 spaces before I start printing my digits. So I'm just going to start with spaces everywhere, and then I'm going to fill in my digits as I find them from here backwards. Okay? That's my strategy. Okay? Strategy. Well, there are actually a couple of things that I'm going to do. First, if x is negative, I'm going to store a flag someplace that will tell me when I get all the digits out there, okay, now I need to put in a minus sign. Then I will work with the absolute value. In other words, I'm always going to be, as I start doing the extraction of each of the digits, I want to work with a positive number. So the very first part, well, there may be some things before this, but I'm going to do this thing. Let's see. Load, let's say register 0 from X. Then I'll say if it's 0 or positive, I'm going to jump out here. Otherwise, I'm going to take the negative of this thing, where I do a not, and then I add a 1. That gets me a negative.
Positive.
And now, someplace I've got to be able to remember that I had a negative number, so that when I'm done, I can come back and put the minus sign on it. Well, okay, I've got to be able to get just a number 1, let's say, stored someplace. I'm going to call it flag. In other words, I'm going to have in here somewhere a memory location flag, which I will start with a 0 in it. If at the end I've still got a 0, that's going to say it's a positive number. Don't worry about the sign. Now, here's the trick, and one of the things that's really kind of limiting about this very restricted instruction set. I don't have anything that will allow me to store something in immediate or literal mode. There are only 2 instructions in the whole thing that use immediate mode: add and and. Okay, so I have to do some fussing to get this flag set in there. Okay, I've got it now then. I'll store register 1, I called it flag. Now I can proceed, you see, as though I had a positive number. Okay, that's the way I handle this business. If it's negative, I save something that I can check later on and put a minus sign on things. But then I change it to the positive thing, and when I get to here, I've got a positive value in register 0, no matter what I started with. 0 or positive, but certainly not negative. Okay. Let's see. I was thinking there was something else I wanted to do before I actually started that load, but maybe not. Here's what I'm going to do. I'm going to use the stack to pass arguments. Now, it's not necessary here, but, oh, yeah, that's what I needed to do first, was to initialize my stack pointer. So we'll have well, let's see, we would actually have our origin thing up here before. Okay, we'll stick with 3,000, which will give us some space for our stack. I'm going to load that address into register 6. That's where I want it. Load effective address, register 6. Begin. Okay, that initializes my stack pointer. So now if I have put this value that I want to work with in register 0. So I'm going to push that onto the stack. I do that by first of all decrementing the stack pointer so that I don't replace this instruction, but I go back one location before. I go to 2FFF, that's where I go, and then I can store relative register 0, register 6 with 0 offset. Okay, that says to push register 0 on the stack. Now I'm going to go to my subprogram and my subprogram is going to divide that number that I put on the stack by 10. Now I need to specify how that thing's going to return the results. Div by 10 will return our stack looking like this. Whatever's down there before, but at the top of the stack I want the remainder, and just below it the quotient. So now, as I come back from this subroutine, I haven't written it yet, I'm postponing that. Put that out of sight for a minute. I'm just going to assume that when I come back from that routine, I have on the top of the stack the remainder, which is going to be, first call, the last digit. And below that is the quotient. Well,
Where's the remainder again on the stack? Is it the
it's
second
on
one?
the top of the stack.
Okay.
So if I do a pop, bring something off the stack, what it's gonna bring in is that remainder. So if I do a load relative register 0, register 6 is my stack pointer. It's got the address of the top of that stack, and I'm not moving away from the top. Now, that's the actual value of that last digit. I need the ASCII code. And since I'm doing base 10, all I have to do is add a hex 30 to it. So I can say add register 0, register 0. Get this right. Oh, wait, though. I can't do that in immediate mode, can I?
Yeah, it's too big.
I've got, my immediate mode is only 5 digits. And that's gonna be too big.
Store the
Okay.
label, load the label.
That's what?
You store the label, load the label, and do.
Yeah, that's what I'm gonna have to do.
Do that.
So again, as I start looking at what I've got to have down here, I have my ASCII, let's say, I have that. Now, I can load register 1. And then do an add register 0, register 1. Now I need to store that thing someplace. Uh-oh. Good thing I left a gap up here. Might even think I was thinking ahead. I want to get the address of this character string into a register someplace. So I will put that in register 5. But I'm going to be filling it from down here at the end back up this way. So I need to add 1, 2, 3, 4, 5. So I will add a 5 onto it. That puts register 5 pointing right here. So that now I can do a store relative register 0, register 5 with no offset. I want to back that register up. Because I've already got the last character here, so now I want to be sure the next time I am here. And just build that string from the end back up toward the beginning. Okay, that takes care of my remainder. Now I want to look at the quotient.
Is that a 0 or a 6? R0,
Zero.
R0?
Let's see.
R0 and then R6.
I've got a problem here. When I popped this value off the stack, I did not adjust my stack pointer, which I should have done. So right in here, we do an add R6, R6, 1. Okay, that's pop the remainder on the stack. I could do it down here, but it's just good practice to always have that stack pointer pointing not at the value you just popped off, but at the next one to come out. Just a good habit to get into. So now I want to get the quotient. So now I load register 0 from register 6 with no offset, and R6, R6, 1. Okay, so here we're going to pop the quotient. Okay. As long as that quotient is not 0, it's never going to be negative. Because remember, I've got the negative taken care of back here. So if it's still plus, I'm going to go back up here and do it again. Okay. It's obviously not done. Well, for one thing, I haven't written the divide by 10 routine. But if we just assume that and just check this and see if our logic is working out all right. Let's just see where we might be. I don't know where these things might be. Let's just say that for the sake of argument that we're at 3100, 3101, 2, 3, 4. This is 3105, 6, 7, 3108. Just so we've got some numbers here to work with. Let's see what happens to us. I don't have a location for X. That's all right. We're still just kind of checking our logic here. Let's see, we use register 0, register 1, register 5, and register 6. Okay, what do we do here? Well, here we load register 6 with the address of begin, which is 3000. Then I load register 5 with the address of string, which is 3101. And then I add 5 onto that, which gets me at 3106. That's this one right here. Okay, so there's register 5. Okay, now we load register 0 from X. Well, for this first run through, let's take a relatively small number, just so that we let's say it's 3A in hex. 3A is 3 times 16 plus 10. That's 48 plus 10, or 58. That's the number that I'm actually working with in decimal. Okay, well it is plus, so I skip all of this stuff. If we have time, we'll look at what happens with a negative number. Now, this says add a -1 to register 6. So that gets us down here to FFF. And then it stores in that location. Here's my stack. Let's just note here that this is 3000. This is where our load effective address instruction is. R6 begin. This is to FFF. This is to FFE. So on. Okay, so when I subtracted 1, that got register 6 here. Now it says store register 0 in that location. Okay, so now I've got a 003A in there. Now I jump to my subroutine. Wave our hands a little bit. What that subroutine is supposed to do is to take that value that's on the top of the stack, divide it by 10, and then put the quotient and then the remainder. Well, it's going to pop that value off of there, so it's going to pull off the 3A, work with it, divide it by 10, it's going to get a quotient of 5. And a remainder of 8. And when it comes back, it will have adjusted this stack pointer so that it's looking at the top of the stack, which is the remainder. So now, as I come back from the routine, what's actually in register 6 is 2FFE. Okay, like I say, now I've waved my hands quite a bit at the subprogram. We'll show you that on Wednesday. We should have time to do that, put that all together and finish off this. But that's what I want it to do. I want that subprogram to pull a value off of the stack, do a pop operation, divide that value by 10, put the quotient back on first, and then put the remainder on. Because that's the logic that I've got going here. If it does it in the reverse order, I'll end up with 8.5 instead of 5.8. You have to be sure that all these things are handled in the right sequence.
Quick question.
Yeah.
So on the LDR, R0, R6, just below the function or
Mhm.
subroutine, R6 is going to equal to FFF.
E.
E.
Because the subprogram will have changed the register.
Okay.
See, as it does the pushes of the values, the quotient and the remainder, it's going to change that stack pointer. The stack pointer is a global variable. It's visible everywhere. If it's not, oh my, you can get some pretty deadly side effects. Because one piece of the program will mess up things that somebody else put on the stack and you won't know about it. Okay? It's got to be, don't touch. Okay, so we come back, we load register 0 from where register 6 is, and so now we get an 8 here, and we add 1 to register 6, so it's now here. To F now. I load register 1 from ASCII, which is a 0030. Add that onto register 0. So now I get a 38 there. And I store that where register 5 is pointing. Register 5 is at 3106, it's right here. Suddenly now, instead of a 20 there, I've got a 38. And I subtract 1 from register 5, right here, so that backs down to 3101, or 3105. Okay, now I load register 0 from where register 6 is pointing. That's here. So now all of a sudden, I've got a 5 in there. I just copied this thing into that register, because that's the address that's in register 6. Add 1 to register 6. We're now at 3000, and so register 6 is now here, right back where we started. I'm going to have to do that in the other order, because this add will change the condition codes that were set by this one. And since my addresses are all up in these high numbers, this result's always going to be positive. I've got to do a song and dance there.
Just add 0 to R0.
I could do that.
Then I'll give it.
Here's another trick. I can increment my stack pointer so that it's down to here. Now then, I can do I can offset -1 from where my stack pointer is and get back to this one. Therefore, I really am copying the quotient when you move that stack pointer, you don't change anything that's actually in memory. The only way any of that changes is if you store something out there. So I change my stack pointer first and then just do this song and dance to get past the fact that I messed it up. Okay, so the last thing I do is that load relative, which will set the condition codes based on the value that's loaded. So it's what goes into register 0. In this case, it's positive. So I go back up here. Now, I subtract 1 from register 6, gets it back to here. I store register 0 out there. Happens to be the value that's already in that memory location, but that's okay. We go to the subroutine, divide by 10. Now, what's going to happen when I divide 5 by 10? I'm going to get a quotient of 0 and a remainder of 5. This is the key, the thing I need. I'll skip through most of this stuff here because we're out of time. What we do is we get the ASCII code onto this thing, and so we get now out of here a 3-5. I again now pop the quotient, but now this time the quotient is 0, and so when I hit this branch I don't take it. Now I can go ahead and do my finishing up stuff, print out the string, and put a minus sign on if I needed one. I'll need to check for that. But this is how you can do decimal output working from 2's complement. Okay? We're out of time. We're past out of time.